Okay, for the next few problems, I'm not going to use the stoichiometry roadmap. I'm going to show you how to work the problems without having to use that as a reference sheet. So number 8, in a blast furnace, iron 3 oxide is used to produce iron by the following unbalanced reaction. If 4 kilograms of Fe2O3 are available to react, how many moles of carbon monoxide are needed? So the first thing we have to do is balance our reaction. Alright, let's see if we put 3. Alright, so there's our reaction. In part A, it tells us we have 4 kilograms of Fe2O3, and we're looking for moles of carbon monoxide. Well, the only other grams we know comes from the periodic table, and it's in grams, not in kilograms. So we need to convert kilograms to grams, and we do that by moving our decimal 3 times to the right. So instead of using 4.00 kilograms, I'm going to use 4,000 grams of Fe2O3. Right. I know that I have grams of Fe2O3 in this box, and I have to have the same units in this box. And the only place I can get grams of Fe2O3 is from the periodic table. So looking at the periodic table, we're going to add the mass of 2 iron and 3 oxygen. And we get 159.7 grams Fe2O3. And anytime we get a number from the periodic table, it's always equal to 1 mole of that substance. So that's why I know to put 1 mole of Fe2O3 on top. So now, if I have units of moles and Fe2O3 up here, I have to have moles of Fe2O3 down at the bottom. And I'm going to get that number of moles from my balanced chemical equation, and if I look, my coefficient is 1. So 1 mole Fe2O3. All right, at this point, I've done every conversion that I can do with Fe2O3. There's nothing left for me to do except change to my new substance. And in the question, it asks how many moles of carbon monoxide are needed. So now I have to use a mole to mole ratio. If I have 1 mole of Fe2O3, I have 3 moles of carbon monoxide. So that's what goes next. The question asks for moles of carbon monoxide, and that's what I had in the top of my very last box. So now I know I can stop. So I'm going to take my calculator and I'm going to multiply all the numbers across the top, multiply all the numbers across the bottom, and divide the two values. And you should get 75.1 moles of carbon monoxide. All right, for B, how many moles of each product are formed? The easiest problems are always mole-to-mole problems. So if a question asks for you to end with moles and there's a way for you to begin the problem with moles, do it. So I could start out using 4,000 grams of Fe2O3, but it's a lot easier if I start out using 75.1 moles of carbon monoxide. So if I have 75.1 moles of carbon monoxide, I'm trying to get to moles of product, and the first product I'm going to do is 2 moles of Fe. So for every 3 moles of CO, I have 2 moles of Fe. I have moles of carbon monoxide here. I can put moles of carbon monoxide down at the bottom, and in my equation, I have 3. From that 3 moles of carbon monoxide, I can get 2 moles of Fe. The question in B asks us for moles of product. Well, I have units of moles. Fe is a product, so I'm done. Plug this in into your calculator, and you should get 50.1 moles of Fe. And then our other product is carbon dioxide. So again, I'm still going to start with my 75.1 moles of carbon monoxide. For every 3 moles of carbon monoxide, I get 3 moles of carbon dioxide. My 3's cancel out, so I end up with the same value, just different units. All right, so that's everything for number 8. Let's look at number 9. Methanol, CH3OH, is an important industrial compound that is produced from the following unbalanced reaction. What mass of each reactant would be needed to produce 100 kilograms of ethanol? All right, so let's balance our equation real quick. I'll write it over here. Let's see. All right, and they've given us our starting number in kilograms. We've got to change that to grams because we can't get a molar mass in kilograms. So if we move our decimal 3 times to the right, and if you want, if it's easier for you to put this in scientific notation, go for it. Most people think scientific notation is confusing, so I'm not going to use it on this one. All right, so if we have 100,000 grams of methanol, we need to know how many grams of each reactant. So I have to stop at grams of carbon monoxide. And so here I'm starting with grams of methanol. I have grams of methanol here. I have to have grams of methanol down here. And the only place I can get that is from the periodic table. So when I add all of that together, I get 32.05 grams of methanol, and everything on the periodic table is equal to 1 mole of that substance. So now that I have my value in moles, I can do a mole ratio. So if I look, for every 1 mole of methanol, I have 1 mole of carbon monoxide. I have methanol at top here, so I have to have methanol on bottom here so it cancels out. All right, so right now, if I were to stop, I would have my answer in moles of carbon monoxide. But the question asks what mass. So I have to change that moles to grams, and I have to do that by using the molar mass from the periodic table. And if I add up carbon and oxygen, I get 28.01 grams. And remember, that's equal to 1 mole. So now if I stop, my units are grams, carbon monoxide. That's what the question is asking for. So I can multiply across the top and get an answer, multiply across the bottom and get an answer, and divide the two values, and you get a really big number. And that's grams of carbon monoxide. Your calculator might give it to you in scientific notation, which would be 8.739 times 10 to the 4th grams of carbon monoxide. Ran out of room, I wrote too big. All right, so that's 87,394.70 grams of carbon monoxide, or 8.739 times 10 to the 4th grams of carbon monoxide. All right, so it wants us to do that for each reactant. So now we get to do this all over again, but wherever we have CO, we're going to plug in the information for H2. So we're going to start, we don't have anything in moles, so we have to start with our grams. All right, so we can just really copy the same information from the previous question until we get to the CO information. All right, so for every 1 mole of methanol, we have 2 moles of H2. So now I'm going to plug in 2 moles of H2 on the top. And they want the answer in grams, so we have to do one more box. And if we add up the mass of 2 hydrogen atoms, periodic table, we get 2.02. And that's equal to 1 mole of O2. I'm sorry, H2. And the question asks for units of mass for our reactants. So that's what we have in the last box, so we can stop. So now in your calculator, we multiply across the top and get an answer. We multiply across the bottom and get an answer. We divide those two values, and we get this is 12,605.30 grams of H2. Or if your calculator gives it to you in scientific notation, it's 1.261 times 10 to the 4th grams of H2. This is the longest type of problem when you're starting with units of grams and you have to end with units of grams. So you have to have 4 different sets of conversion factors to get through those. So those will always be the longest ones. All right. I'm going to skip 10 and 11 because you're doing the same steps as previous problems. Number 12, the double replacement reaction between silver nitrate and sodium bromide produces silver bromide, a component of photographic film. All right. So we need a balanced reaction. We know that we have a reaction between silver nitrate, AgNO3. They both have charges of 1, so they cancel. And then sodium bromide, NaBr, they also have charges of 1 that cancel. And so now our 2 positive ions are going to trade places, and Na is going to break its bond with bromide and bond with nitrate. So we have NaNO3 plus AgBr. Since everything has a charge of 1, we don't have any coefficients. All right, so question A says, is a 4.50 mole of silver nitrate react? What mass of sodium bromide is required? So we're going to start with the number that's given, 4.50 moles of silver nitrate. All right, since our value is already in moles, the next step will be to do a mole ratio. So if I have 4.5 moles of silver nitrate in my balanced reaction, for every 1 mole of silver nitrate, I have 1 mole of silver bromide. Whoops, nope. Question A says sodium bromide. That was right, sodium bromide. So 1 mole of AgNO3, 1 mole of NaBr, and the question asks for mass instead of moles, so we still need to do another box. So if we look on the periodic table and we add together the masses of Na and Br, we should get 102.89. And everything on the periodic table is equal to 1 mole of that substance. So now our units in our compound match what's asked for in the question, so we can stop. We multiply across the top. We divide by what's on the bottom. And you should get 463 grams of sodium bromide. All right, and then question B, what mass of silver bromide is formed? So, move this down a little bit. It's always easiest to work with units of moles, so I'm going to still use my 4.50 moles of silver nitrate. Now looking at my balanced reaction to get a mole ratio, I'm using silver nitrate and silver bromide, and it's still a 1-to-1 ratio. So we put the silver nitrate on bottom so it'll cancel out with the silver nitrate on top. And put silver bromide on the top. And it wants it in grams. We're looking for mass, so we need our molar mass from the periodic table. So add together the masses of Ag and Br. We should get 187.77 grams. The bottom should be 1 mole. Alright, if we look, we have grams of AgBr, and that's what the question's asking for, so we can stop. And we plug all of this in our calculator, and you should get 845 grams of the AgBr. Right. That's the last sample problem that I'm going to work out of section 2. The next video, I'll go over section 3 of limiting reactants and percent yield. And then I also have some problems on conversions from moles to liters that you will need for the second worksheet that I handed out.